Okay, so let's start. So welcome everyone in the Zoom and you that you're in the room. This is the first session on fine-tuning large language models, or in short, LLMs. So I'm Oren, and I'm a computer science PhD candidate at the Hebrew University, working on analogical reasoning under the supervision of Professor Daphne Shachaf. In addition to my academic work, I'm also a researcher student here at Lightricks under the data science group of ASI, where I'm now working on a research related to LTX Studio. Okay, so our agenda for today is divided into two parts. We will start with a fine-tuning overview lecture. Then we will have a short coffee break. And then we will have a fine-tuning code example in which we will fine-tune a model to be a medical diagnosis model. In the next session, scheduled for next week, I will talk about a real use case from Lightricks involving fine-tuning that was deployed in VideoLeap, and also this work has led to a research paper that has been submitted to EMNLP 2024 conference. Okay, so what will you learn today? So you will learn what is fine-tuning and how to fine-tune an LLM. And you will learn what are the scenarios when we want to use fine-tuning and when we don't want to use fine-tuning. So I know you have already learned about different approaches like prompt engineering and RAG. So my goal here is to emphasize what are the scenarios to use each one of the approaches. In the second part, you will see how to implement supervised fine-tuning in code. And lastly, we will talk about the challenging and complex topic of how to evaluate an LLM. So I will talk about like the general perspective you should consider in evaluation, and also what are the different methods to evaluate LLM. Okay, so let's begin with the overview lecture. Okay, so before I can talk about fine-tuning, so first the model needs to exist in the first place. That's why I want to start the talk with pre-training, which is the first phase. So the model at the start has zero knowledge about the word, and it cannot form English words. And these models are usually trained on the task of next token prediction, using a giant corpus of text data from the web, which is unlabeled. This training objective is often called self-supervised learning, because we don't need to label the data. The model can just utilize the huge amount of text data in the web and supervise itself for this task. So here you can see an example of a sentence that we have from the web: once upon a midnight dreary while I pondered. And the goal of the model is to predict the next token after once. So you can see that in the beginning, the model predicts something which is meaningless. But after training, the model predicts correctly the next token, which is upon. So after training, the model learns language, and it learns a huge amount of knowledge from the web. Okay, so now that we have a pre-trained language model, we can talk about fine-tuning it further. So what is fine-tuning? Fine-tuning is taking the pre-trained general purpose model and train some of its weights. So this is like a general definition. And in the context of LLMs, fine-tuning is taking the general purpose base model and transform it to a spatialized model for a particular use case. So what's the difference between fine-tuning and prompt engineering in short? So in fine-tuning, we get the model to learn the data. We're actually adjusting the model weights, rather than in prompt engineering when we just have access to the model. In addition, in fine-tuning, it lets us put as much as we want data in the training process, as opposed to prompt engineering when we know that we have the context window limitation. And what's the difference between fine-tuning and pre-training that we saw in previous slides? So the main difference is that fine-tuning requires significantly less data and computational resources, because think about it, in the pre-training phase, so we train all of the parameters of the model, and we use huge amount of text data from the web. So the pre-training phase belongs to only like a few big companies that invest a lot of efforts to do it. And many other companies, and also in academia, the fine-tuning is much more popular because we need only a small amount of data, and we need only to adjust like a subset of the parameters, or as you will see later, we can adjust just new additional parameters. And this is the diagram to illustrate it. So we have the pre-trained LLM, and then if you want to fine-tune, we use probably a data set to fine-tune, and we create a fine-tune LLM. So we actually create a new model in fine-tuning. Whether in prompting, we just have the access to the pre-trained LLM. Okay, so now yeah, question. Mm-hmm. Self-supervised, yeah.
Can you please repeat the question?
Is in process. Yeah. Okay, so self-supervision is one of the options to do fine-tuning. We will see later what are the different ways to do fine-tuning. And you're right. Also we can do fine-tuning with self-supervised. I will show later a scenario, but we can do fine-tuning with regular supervised learning, okay? That we collect the data. So we have a slide about it. Okay, so now I want to show you examples of what's the difference between a base model completion and a fine-tuned model completions. So let's take in this example GPT-3, which is a base model, and ask it how to fine-tune a model. And the completion will look something similar to how can I control the complexity of a model, how do I know when my model is done, and some other related question to our question. But this completion is actually not what we want. We want an answer for our question. But since GPT-3 is a base model, and it was trained on the next token prediction task, so it's probably see these other questions in the same homework assignment or Google search queries. On the other end, if you will use the fine-tuned version of GPT-3, which is ChatGPT or GPT 3.5 Turbo, and ask it the same question, how to fine-tune a model, so we will get a much more helpful completion, like fine-tuning a model typically involves taking a pre-trained model and further training it on a new data set specific to your task. Here are the general steps to fine-tune a model. So you can see in this example that by fine-tuning, we can actually change the behavior of the model to be more desirable, more practical, and helpful completions. And a cool analogy that you can think of is that the GPT-3, the base model, is like the raw diamond. And what we are doing, actually, we transform it to something which is more practical. For example, something that you can put on your diamond ring. So this is like ChatGPT. Okay, second example. Now let's take, for example, symptoms of some patient. So we have skin irritation, redness, and itching. And we are asking a base model LLM, what are these symptoms? Like, give me some diagnosis. And the LLM say, it's probably acne. So this is like a general response. But now, on the other end, we fine-tune the LLM on some dermatology data, and giving the same symptoms, we will get, as you can see here, after training, a much more in-depth and specific answer, such you have a mix of non-inflammatory comedonal acne and inflammatory papulopustular acne. So in this example, you can see that we can change the knowledge of the model. And a cool analogy for this example, you can think of the base model as the primary care physician and the fine-tuned model. So for example, the model that was fine-tuned on dermatology data as the dermatologist, who is a medical doctor specialized in conditions related to the skin, or cardiologist, who is a medical doctor specialized in conditions and diseases related to the heart. Yeah. We will have a slide about comparing fine-tuning and RAG. And if I'm not answering you, ask again. Okay. So after we saw what is fine-tuning and like two examples of fine-tuning completions, And before I'm going to compare fine-tuning, RAG, and prompt engineering, I want to give you the main motivation for fine-tuning. And this is that a smaller fine-tuned model can often outperform the performance of a larger, more expensive model on the set of tasks on which it was fine-tuned. Okay, so here is, for example, a paper from the OpenAI, training language models to follow instructions with human feedback. In this paper, OpenAI fine-tuned InstructGPT, which is a much more smaller model than GPT-3. And they fine-tuned it to better aligned with human responses. And they got a fine-tuned model which is much better for the task. Okay, now let's compare, first of all, prompt engineering and fine-tuning, okay? So I know that you learned about prompt engineering in the beginning, and actually I always recommend you to start with prompt engineering because it's very easy to get started with, and also it gives you a sense of the current capabilities of your LLM, okay? Now, some advantages of prompting is that no data or very few is needed to get started. And there is a smaller upfront cost. So all you need is just a few API calls, and it's nothing like in cost. And also there is no technical knowledge that is needed. All you need to know is how to write a prompt. And there are other tools that can help you to write prompts today. And also you can ask ChatGPT, please help me to rephrase or rewrite the prompt so the model will better understand. On the other end, in fine-tuning, more high-quality data is needed, which is expensive. And there is an upfront compute cost because we need the training, we need to use a GPU, so this is more expensive and complex. And actually, we need some technical knowledge, also in the data preparation part, but also in the how to train the model. So we need some NLP and machine learning knowledge. Okay, so now back to prompting. In prompting, much less data fits. So all of us know that different models has the context window limitation. And also, if you write a very long prompt, so research shows that models tends to forget knowledge which is far away in the context. So also, if you manage to write a long prompt, they can forget some of the data. And one of the biggest problems in LLMs, and it's especially popular in prompt engineering, is the hallucinations. So LLMs tends to make up stories and write incorrect data that does not exist. On the other end, with fine-tuning, so we have nearly unlimited data fits, so we can choose how many samples that we want for the training, and we can learn from the data. So a cool use case, for example, is to learn from user behavioral signals. So we can have in our fine-tuning set data that we know that is aligned with our users. So we create a model which better serves our users. And last thing, so usually you want to fine-tune with the smaller LLMs. So the less, we have a less cost afterwards if the LLM is smaller. And also we have a lower latency. Okay, so the response will be faster because it's smaller model. And smaller models also means that we need a chip like GPU, and we can serve how many users that we want for how many requests. On the other end, think about deploying GPT-4 in production with long prompts. So where we have more calls and more users, we will going to pay much more. Okay, so in general, to conclude, prompting is for generic side projects and prototypes. And again, I always recommend you to start with prompt engineering. And fine-tuning is more for domain-specific, enterprise, and production usage, since we have the low cost and lower latency. Okay, so if you want to summarize the main benefits of using your own LLM, to fine-tune your own LLM, so we can divide it into performance. So fine-tuning helps us to decrease the hallucinations, also to increase consistency in the responses. So if you want the model to respond with some JSON format, which is very complex, so if you use fine-tuning, after the model will see some example from the data, it will understand from the data what is the JSON format that is needed. But if you use prompt engineering, you are more prone to mistakes. Okay, the second category is privacy. So when you're fine-tuning your own LLM, so this is on-premise, and you prevent data leakage to a third party. So some companies, it's very important to them if they have sensitive or confidential data. And the third category, I've talked about it, it's the cost. So we have lower cost per request, and it also helps us to increase the transparency and to control our budget. Yeah, question.
Yeah, so I understand that you're updating like the weights of the model, but how do you make it smaller?
Okay, so in fine-tuning, usually you want to be specialized in one specific task. So you don't need to be good in everything. So the larger models like GPT-3, so they have a great knowledge on many topics. But if you want to fine-tune the model to be specific, perform well on specific tasks, so usually by giving some data in training, you can use very small language models, like with millions or hundreds of millions of parameters instead of billions, and still it perform well.
But do you like take the large model and in some way like prune parts of it, or?
Okay, so there are different types of fine-tuning. So what you say, it's called distillation, that you can take the answers from a larger model, create the data, and then fine-tune the smaller model. But now I'm talking about, in general, you can take a small model, give it some data, and then it will be fine-tuned and very good in this specific task, thanks to your data. And it makes sense because it doesn't need to be good in everything. Actually, distillation we will talk about in the next session. Okay, so we talked about the cost, and the last thing is reliability. So now that one more advantage is that if we have our own fine-tuned model, we control the uptime of the model. We are not dependent of to use closed model, which can be deprecated or shut down. Okay, like Text DaVinci 003. If you remember, it was deprecated and shut down, and you need to know it. If you want to deploy it in production, it's a bit problem. In fine-tune model, it's an open source model. It's in your premise, and you control the uptime. Again, lower latency. And last thing is moderation. So moderation is all of the responses like, I'm sorry, I can't answer about it, or this is an inappropriate request. So instead of using a closed model with its own style of responses, you can fine-tune your own model to respond to your users how you want. Okay, now for the question of what's the difference between RAG and fine-tuning. Okay, so let's start with RAG. So RAG is much better in integrating new dynamic knowledge. So if your data has a lot of changes, and this is a dynamic data, so RAG is the solution for you. For example, a question answering system about the current events, like the news updates. So you will not use a fine-tuning. Also in RAG, you have no training and no retraining needed, because you use the external data source, which getting updated, but it's not like in fine-tuning, where you fine-tune with some data, and then if you have a new data, you need to train it again to get the model update. And also with RAG, you have more accurate responses, and it reduces hallucinations much more, because think about it, in RAG, it realizes the answer realized on specific document. So it also helps you for explainability, because you can track where the answers come from. And it also reduces the hallucination, because you give it like a specific document that you should rely the answer on this document. On the other end, with fine-tuning, it's not suitable for learning evolving knowledge. Okay, so if you have changes in the data, fine-tuning will be a problem. And fine-tuning is more expensive. We need high-quality data, and we need retraining from time to time. And it's still prone to hallucinations. Okay, now some downsides of RAG. So it's slower. Now we have two-step process. We have the component of the retrieval and also the part of the generation. And in general, if you have high-quality data and specific task, usually RAG will give you lower performance than fine-tuning, okay? This is the part that fine-tuning is specialized for. And also RAG is not suitable for changing the behavior. So you remember that we fine-tune a model to be a chatbot or response with a specific style or tone. So RAG is not for this. This is fine-tuning. Okay, and then again to fine-tuning, so optimize the LLM performance for specific task. And since we have the precise control on the training data, it makes it possible to adjust the tone, the style, to aligning with user preferences, and also controlling the output format much better. And we can, as we talked before, to improve the efficiency by using smaller LLM for better latency and cost. So to conclude, RAG is for generic context-heavy tasks with dynamic knowledge integration. And fine-tuning is for improving the performance on a specific task. So back to your question. Is it answer your question? Or cool. Okay. Okay, so we've seen like yeah, question. Okay, so what's the amount of data you need for fine-tuning? So it's an important question. And of course, it changed from task to task. So the answer for me, so in my experience, like I successfully did fine-tuning and succeed in the task with thousands of examples, for example. But it really depends on the task. And usually if you have more data for fine-tuning is better, it will not get you damage. And you need to see where so you need some evaluation metric and you need to see when it converges. Okay, so this is the way to know how much data is needed. But it's not only on the amount of data, as we will see later, it's the quality of the data and how much the data is diverse. So there are a lot of consideration. Amount is only like one dimension to look at it. Okay, so now back to the question of self-supervised and supervised fine-tuning. So here I'm going to give you all of the ways to do fine-tuning. So the first way is indeed self-supervised. So we have training data and we train the model on the next token prediction task. And for example, if we will get the sentence, Houston, we have a, and we train the LLM, probably it will answer with the token problem. So we have seen it in pre-training. But this also can be useful in fine-tuning. For example, if I'm a writer or an author and I write papers and blogs and I want to fine-tune a model to write in my style, so I can fine-tune a model with all of my blogs and papers, and then it will learn how to mimic my style of writing. Okay, the second option to fine-tune, which is by far one of the most popular one, is supervised fine-tuning. In this option, you need to collect the data. So you collect input and output pairs. So for example, if you want to fine-tune for question and answering, so you collect input will be the question. For example, who was the first president of the USA? And the output will be the answer, George Washington. And this is how it looks like. So this is like a sample from the data set. So we have the question, the answer, and some prompt template. For example, please answer the following question. So some instruction. So this is how it looks like, a sample from the data. And why we need to fine-tune for question answering? So as you remember, if I will take a base model and ask it this question, probably it will give me other related question. But by fine-tuning it, that in the data I see that I mean for getting an answer, so I successfully change his behavior, and now if it's a new question, he will try to give me answer. So this is like, again, the change in behavior. Okay, and the third option is using reinforcement learning. So this option, I'm going to show you how OpenAI use reinforcement learning when they launch ChatGPT as part of their training process. So in general, we have the fine-tuned model, and then we have some reward model. So the reward model learns to give a score for a completion for a prompt, that the score evaluates how much it aligns well with humans, okay? So this is the goal of the reward model. And then we use reinforcement learning with some algorithm. So PPO is for proximal policy optimization, which is famous algorithm in reinforcement learning in general. And the idea is that we can, given a new completion of the model in training, we pass it to the reward model, we're getting some score, and use this score as a feedback for the model to update its parameters. So here's a figure from OpenAI paper, training language models to follow instruction with human feedback. So you probably heard about RLHF. So RLHF stands for reinforcement learning from human feedback. And the goal is, as we said, to improve the alignment, performance, and safety of LLMs by incorporating human judgments into the training process. So we can see here in step one, what they did, they collect the demonstration data. So given some prompts, they use humans to write a desired output. Okay, so this is like a real data that humans wrote for them. And then they use this data to fine-tune GPT-3 with supervised fine-tuning. In the next step, they collect comparison data. So now given some completion, so they call the model and got some completions for the same prompt. And they give all of these completions for human to rate which completion is better than the other. So actually the task of the annotator was given 2 completions, just choose which completion is better. And then they have a lot of data of different completions for a prompt with the rating, which completion is better than the other. And they use this data to train the reward model. And in the last phase, they optimize the policy. The policy is like our LLM. So given a new prompt, we give the policy, it generates the outputs, and then this outputs goes to the reward model to evaluate it. And then the reward goes back to the LLM as a feedback to update its weights in order to have LLM which is better aligned with our humans. So of course there are other methods to do it. Right now, after ChatGPT, we have new papers like DPO and other methods that don't need the phase of reward modeling. But this is just for example, and it's very popular. And I'm not going to dive into the details of the PPO algorithm. It's not in the scope, but I want to give you intuition. How can we use reinforcement learning in our context? So in reinforcement learning in general, what we have is the agent that plays in some environment. And then this agent can take some actions. Given some state, it takes some actions, okay? And then it got some rewards, and it tried to maximize the reward to follow some objective. So reinforcement learning is very popular in games, for example, Snake, chess. We can use reinforcement learning. So the player is like the agent. And in our context, so the agent is the LLM, and the environment is the LLM context. And the actions the LLM can take is to choose a token from the available vocabulary dictionary. And the state is like the current context so far. Okay, and the LLM trying to maximize the reward to generate aligned text for humans. Okay. So we have talked about different ways to fine-tune. Now let's talk about what are the ways to parameter training. So our first option is to retrain all of the parameters, and this is also called full fine-tuning. Now this option is computationally expensive because we are training all of the parameters, and also we are more prone to the phenomenon of catastrophic forgetting. So catastrophic forgetting is the phenomenon which maybe your fine-tuned LLM is really good on the new task and learns the new information really well, but it forgets previously learned information. And this will happen if you, it's more to happen if you do like full fine-tuning because you update all of the model. The second option is transfer learning, where you freeze most of the parameters and fine-tune only parameters from the last layers. So in this option, you train only subset of the parameters. The third option is parameter-efficient fine-tuning, or in short, PEFT. And in this category, a very famous method called LoRA that we will explore soon. So in this method, we freeze all of the parameters, and we only augment a relatively small amount of trainable parameters. Okay, now before I'm going to talk about LoRA, I have to mention this revolutionary paper in NLP and also in deep learning in general. Yeah, question.
A clarification, do you mean like you add a few more parameters and you train them? It's a new one. Like
yeah, it's a new parameters. Okay. Yeah. Okay. So before talking about LoRA, I want to mention this paper, which is, of course, Attention is All You Need, which revolutionized all of the field of NLP and deep learning in general. And why I mentioned this paper, because all of the LLMs, or most of them that you see, are based on one of the variation of the transformer. So the credit goes to Google and University of Toronto that released this paper 6 or 7 years ago. So this is the main figure from the paper. Here you can see the transformer architecture. and they demonstrate it with the task of machine translation. So you can see a sentence in French. So these are our input tokens. So computers and models, they don't understand text, of course. So we need to somehow convert it to numbers. So this is called tokenization, which you will see soon. So we get the tokens IDs for these input tokens. And then we will get the embedding by using the embedding matrix. Now, one of the key innovation in Transformer is that all of the input tokens are digested in parallel. That's why we have a positional encoding mechanism to get a notion of what's the order of different tokens in the sequence. Now, the main components in the transformer is the encoder blocks, which are responsible for build the representation of the input, and the decoder blocks that are responsible to generate the output tokens. Okay, so now I will show you like different families of models. Okay, and one thing that I forgot, the key innovation in Transformer is the self-attention mechanism, of course. And this is, as you can see, also in the encoder and the decoder. And the self-attention mechanism is a neural network that is responsible to give some score or weight for every token in relative to the other token. So it gives us like a weight, how much we need to attend to other token, how much energy we need to give to the other token from every one token. And this attention mechanism enables the transformer to have long-term relationships and learns well the overall context, which was a big problem from previous approaches. Okay, so now let's see the different variations of transformers. So we have encoder-only models, also called autoencoder. These models like BERT and Roberta for tasks like sentiment analysis and named entity recognition. And the training objective is to predict the mask token. This is also called denoising objective. So in BERT, for example, in the training, we have a sentence, and then we have mask above some of the tokens, and the task is to predict these mask tokens. The next group is decoder-only or autoregressive models. So these models just taking the stacking of the decoder blocks of the transformer. So the previous ones, only the encoder, now only the decoder. These models like GPT and LLaMA, and this is mainly for text generation. Now the training objective now is to predict the next token. And in training, they cannot see the tokens from the future, okay? Because if we will show them the tokens from the future and this is the task, so there will be no learning. That's why we need to hide the future tokens in training. The last one is the encoder-decoder or sequence-to-sequence. So this is the full architecture of the transformer, and this is like the original architecture also in the paper. And this is mainly, as we talked, for machine translation, but also for summarization and question answering. And models like T5 and BART. And the training objective, for example, in T5, is to train the encoder by span corruption. So in span corruption, we mask few adjacent tokens and not only one token. Then we replace the mask tokens with a new token, which is not part of the dictionary. And then the decoder's goal is to reconstruct the new token that we masked. Okay, now let's talk about LoRA after we have like this overview. So LoRA stands for low rank adaptation, and the motivation is to make fine-tuning more feasible. So thanks to LoRA, all of us can make fine-tuning. Fine-tuning more feasible means to reduce the computational and storage required with full fine-tuning. And as you can see here in LoRA, so we have the frozen weights. We freeze all of the LLM weights. And we have some two low decomposition matrices, B and A. And we train the weights only for the smaller matrices. And in training, this is in training. And now in inference, we multiply these matrices and add them to the original weights. And the multiplication of these matrices is also called the diff weights or delta weights, because this is the weights that we need to move from the original weights to the weights after the fine-tuned model. Okay, and let's see an example to illustrate LoRA. So here we have W0, which is the original weights, which are frozen. And here we have B and A, which are the trainable parameters. And the multiplication of B and A, as you can see, is delta W. And delta W and W0 are from the same dimension because we need to add them together. And let's take, for example, the dimension to be D by K, such that D is 1,000 and K is 1,000. So we have 1 million parameters frozen. This is the original one. And let's take rank to be 2 in this example. So we have for B 2,000 parameters and for A also 2,000 parameters. So in total 4,000 parameters, which is much slower than 1 million original parameters. So you can see how much parameters we save by using LoRA. And as you probably understand, the R is hyperparameter. And if we choose R, which is too low, so maybe we will save a lot of parameters, but we will lose information because we are going to delete probably independently rows in the matrix. On the other hand, if we use R, which is too high, so we will not significantly reduce parameters, and we will have like dependent rows. And what is cool about LoRA is that we can use it for different tasks. So if we want to fine-tune a model for task A and then fine-tune model for task B, so we don't need to copy all of the model parameters for every new task. We have the original weights frozen and just add the new adapted weights. Okay, and last slide before the break. So now I want to emphasize that fine-tuning actually is an iterative process. So first of all, you need to start with your base model that you want to fine-tune. Then you have the phase of data preparation where you collect inputs and output pairs for your supervised fine-tuning. Then you move to the training part. Here you can choose to use LoRA or not if it's a small model. And here you have all of the part of hyperparameters tuning and how to train the LLM. The last part is evaluation, where you evaluate the model and see if you're satisfied with the performance. And it will never be the case that in first time you're satisfied and everything is amazing. That's why it's an iterative process where you probably will try to add new data or changing the data a bit. And then also in training, you can change if you use LoRA or you're not using LoRA. And also if you use LoRA, you have the R parameter that you can play with and other parameters like batch size and epochs and all of the things that you know for machine learning. So usually you need some iteration till you're getting a model that you are satisfied from the results. Okay, now let's taking a short coffee break. Yeah, 5 minutes. לא שומע? איפה זה פה? כן זה, כן זה. Okay, so let's continue. יאללה, יאללה. Okay, so welcome again for our second part for today. So, yeah, record. Okay, so in this part, we are going to fine-tune a model. So we'll take LLaMA 2 7 billion chat, which is an already fine-tuned version of LLaMA 2 7 billion base model. And this model released like 1 or 2 years ago by Meta AI. And we are going to fine-tune it to be a medical diagnosis model on a patient-doctor interaction data. Okay, so patient gives some symptoms and the doctor apply with a nice response that is relevant. Okay, so a bit about LLaMA 2. So LLaMA 2 actually is a suite of different pre-trained language models in different sizes from 7 billion, 13 billion, and 70 billions by Meta AI. And these models belongs to the family of autoregressive or decoder only. So it's just stacking of decoder blocks from the transformer. And it's this, maybe a bit changes, but as you can see the architecture on the right, we have block 2 to n, so just used the transformers and the decoder parts. And LLaMA 2 chat is a fine-tuned version of LLaMA 2 for a chatbot, for question answering. So similarly to what OpenAI did with ChatGPT, Meta AI did with LLaMA 2 chat. They use RLHF to align with human preferences for safe and helpful completions. So we have the base model GPT-3, which is analog to LLaMA 2, and we have our fine-tuned model as a chatbot, GPT 3.5 Turbo or ChatGPT, which is analog to the LLaMA 2 chat. So what are the main differences between LLaMA 2 and GPT-3? So first of all, LLaMA 2 is an open source model. It means that we can access to the code repository in GitHub and to see everything with the model, which is amazing. LLaMA 2 was trained on public data, so we know which data the model was trained on, as opposed to GPT, that OpenAI, they don't give us the specific details. LLaMA 2, as you notice, has a smaller architecture in terms of number of parameters, so at most 70 billions, where GPT-3 is 175 billions. But it trains on much more training data, and this is the main difference between them. So even though it has smaller architecture, since they train it on much more data, LLaMA 2 shows comparable and sometimes even better results than GPT-3. Last thing, which is important, is the fast inference. So LLaMA 2, since it's a smaller model with smaller amount of parameters, so we can enjoy the lower latency, which is important for production. So we will prefer LLaMA 2 and not GPT-3 for production usage. Okay, now before we can start, so now I'm moving to the code part. So if you want to start working with LLaMA, specifically LLaMA 2, you need to register in a Meta AI website to request an access for the model. And then they will send you an email with, after like 1 or a few days, they will send you an email with instructions how to get the access for the model. And then it's optionally, but very recommended, to open your account in Hugging Face. And in Hugging Face, we can see all of the models that we can have access, specifically also LLaMA. So we log into the Hugging Face and authenticate with the confirmation email from Meta, and then we can access the model from Hugging Face. So we have some installation and setup. So I will moving like very fast about it. So we have the accelerate for facilitating deep learning training on different platforms. We have PEF that we saw before for parameter efficient fine tuning because I want to use LoRA. We have the bits and bytes, which is a library of Hugging Face for memory optimization. So this is for quantization that we will see soon. We have, of course, the transformers. And here we have TensorBoard to show the results and monitor the training process. But I personally recommend you to use weights and biases to monitor the training process and the evaluation results. And here we're importing the dependencies. So we have Torch for PyTorch. We use the load datasets to fetch the training data. And we import some important classes from the transformers. So for example, we have the auto model for casual LM. So if you see casual LM, it means for text generation, models that are decoder only, like LLaMA and GPT. So by using auto model for casual LM, we can load the model. And we have here like bits and bytes config and training arguments. So you will see it later in the code. So now we import all of the things. And the first thing we want to do is to load the model. So think about it, LLaMA 7 billion, it's like 7 billion parameters. We need it to put inside the GPU. So it's a lot of memory. And the motivation to use quantization is because we want to leverage these advanced models, which are usually very big, and we don't want to be hindered with memory constraints, okay? So what is quantization? Quantization is a technique in which the precision of the model parameters or weights is reduced. So we reduce the precision to make a model smaller and more efficient. And it's often at the cost of slight reduction in accuracy. So as you understand, there is a trade-off. So if you are totally not precise, so maybe you save a lot of memory, but you sacrifice a lot in accuracy. So you need to find the sweet spot in the middle. And let's see example. So if we have 7 billion parameters in floating point 64, 8 bytes precision, we need 56 gigabyte of memory, which is a lot for 7 billion parameters model. So our solution is to use a bits and bytes library from Hugging Face, which allows us to dynamically adjust the precision used when loading the model into memory. And it's important to note that it's irrespective of the precision for the training. So we have two types of precision. One precision is just for loading the weights of the model, and another type of precision is for the computation in the feed-forward pass of the training. So here you can see the configuration for quantization. So first of all, here's the model name that we have in Hugging Face. So we load it into the first GPU. And here we have use 4-bit true, which means we want a precision of 4-bit for our parameters of the model. And we have a compute data type of float 16. As you can see, we can have different precision for the computation. And the last thing is quantization type. So there are two types. There is the PF4 and NF4. And the NF4 is like, it's more advanced, and it means to normalize the values of the parameters before quantization, and it's for more stable quantization. Now, important thing to note is actually that if you only want to load the model and make inference, so you need to leave room for the parameters. But actually in training, you need much more memory. In training, you need actually 3 to 4 times more memory than for only inference. Because in training, you need, in addition to saving the parameters, you need to save the gradients and the optimizer states. So keep it in your mind to leave room for the training. And this is in the code, like very easy. You have the bits and bytes config. You initialize it with all of the configuration. And then we use the auto model for casual LM from pre-trained. We give it the model name, device map, and the BNB config. Okay, next thing we need to care about is the tokenization. So we have seen it in the example with the transformer architecture. So the tokenization is the process of converting the text into a sequence of integers, such that each representing a specific word, a subword, or a character. And you can see here, fine-tuning is for fun for all. This is like the input sequence. And for example, we have the entire word fine, which has its own token ID, but the ing is a subword. But since ing is very popular in English as a subword, so it's more efficient to give it a specific token ID. Okay, so we convert the tokens to their IDs. An important thing to care on is that when you fine-tune when you use tokenizing your data, so you need to use the same tokenizer as the tokenizer that was used for the model that you are trying to fine-tune. Okay? So otherwise there will be a mismatch and the fine-tuning will not work. So you need to be with the same tokenizer. Okay, so we use the auto tokenizer from pre-trained, give it the model name, and then we get the tokenizer. And the next thing is the padding. So usually, neural models and specifically transformers, they expect the input data to be in fixed size batches. So in order to ensure consistent dimensions, tensor dimensions, so we are using padding. So padding is just if you have shorter sequences in the batch, you're adding the padding till reaching the fixed size of a sequence in the batch. So it's a special token. And padding side right means that we add it to the right of the sentence. Okay, so now let's write a function to make our first inference with the model. We have the model, we have the tokenizer, we can start make our first inference. So I recommend you always like check that the model works with generic prompt like how are you there? And then I also recommend you before fine-tuning, take your data, take relevant samples and evaluate the model and see how it responds, what is current capabilities before fine-tuning. Okay, so here we have the pipeline. We pass it the model and the tokenizer for text generation. We got the generator, which is a function, and we pass it to the display response. So in the display response, we first extract the where the instruction start index and where the instruction end index, and then we take all of the substring from the start to the end. So we extract the instruction. Okay, so we extract the I, how are you there, how are you? By the way, the inst and /inst is a formatting specifically for LLaMA, which helps it to understand when is the end of the instruction. Okay, and this is only for the first use, but this function will be for the future use. So here we have the prefix as a medical doctor, respond to this patient query, patient. And if the instructions start with this prefix, so we want to take for the instruction everything which is after the patient. So all of the symptoms that the patient complain about. But for now, we have just the generic message of how are you there? So we're not going to this condition. Okay, so we have the generated response, which is a list of dictionaries, and we access the generated text. So in response text, we have all of also the instruction, but also the response. So now we want to extract only the doctor response. So we take what is after the /inst, and this is how it looks like. So, hi, how are you there? How are you? And this is the response of LLaMA 2.7 billion chat. Hello, I'm just an AI. I don't have feelings or emotions, so I can't experience emotions like humans do. I'm here to help answer your questions and provide information to the best of my ability. How can I assist you today? So a very typical response of chatbot LLM. And as I said before, also check your model with some relevant samples from your data to get a sense of its current capabilities before you're going to the fine-tuning. Okay, so we successfully loaded our model. We did the first inference. Now we want to start with the fine-tuning. So the first thing we need to do is to prepare our data set. So we have a data preparation part, okay? So actually there are two options for data source. Either it can be your own data set, or it can be an existing data set, for example, a data set that exists in Hugging Face. Okay, what kind of data we are aiming for? So I think we talked about it before. It's not only the amount. Of course, we want more data, but we want the data to be in high quality, and we want the data to be diverse. So don't include examples which are very similar to one another, because the goal is that the model will generalize to unseen data. So if you have, for example, a task of multi-class classification, so include as part of the samples labels of the different classes. So the model will have the chance to see different inputs and outputs. Okay, we prefer real data, but of course we can work with generated data by models. And we prefer more data for fine-tuning. It will not damage. And as I said before, you should see when it's converged, like your performance. Okay, now what are the steps to prepare your data? So first we collect the instruction response pairs, and then we concatenate the pairs and add the prompt template. So as you saw before, we have like the prompt template of the instruction. In the question answering, we have please answer to this question, and then we have the question answering. So always we need some instruction in addition to the input output. Then we need to tokenize the data, like padding and truncation. And then finally to split the data into train and test. Okay, so let's load our data set. So here you can see the data set name in Hugging Face is patient doctor. And we use the load dataset function to load the data. For this example, I random sample 3,000 samples from the dataset. And now there is an important part you should do, which is converting the samples of the dataset to some template. So we want in the end a data frame with one column text that will have all of the things we need in the sample. So sample looks like inst, and then the instruction, and then the symptoms of the patient, /inst, we finish the instruction, and then the response of the doctor. So you can take a look at the template dataset function. So we have a sample, which is a dictionary, and we access to the doctor. So sample doctor is the response of the doctor. So we have a clean response, and then we write the instruction as a medical doctor, respond to the patient query patient, and we inject the sample patient, which will give us from the dataset the symptoms of the patient or what the patient wants from the doctor. And then we add a new key for the dictionary. So this is the new column in the data frame, text, which will be the concatenation of the instruction and the response and the end of string token. So finally, what we will have one column text, because as you see here, there is a remove column, so we will remove the other columns. So that's what we need. We need one column with everything that is related to the sample, also the instruction and also the response. And since we're fine-tuning, so we create a new model. So let's give it a better name. So LLaMA 7 billion medical assistance. This will be our new model. And let's get impressed from a sample from the dataset. So this is how it looks like. There is a patient. He says, my 5-year-old daughter is 5 days post tonsillectomy. So tonsillectomy is a kritat shkedim. After the surgery, she seemed to have a lot of nasal mucus and developed a cough that is very wet. I can hear the mucus in her chest. Is this normal after a tonsillectomy? Okay, so the patient just asked if the symptoms are normal after the surgery. And let's see the answer. So this is from the dataset. It's not answer from the model, but it's answer that we are trying to fine-tune a model to be similar to. So the answer from the dataset: hello there, as a medical doctor, I understand your concern about 5-year-old daughter's post-tonsillectomy symptoms. It's common for children to experience nasal mucus and coughing after tonsillectomy. And in most cases, these symptoms are normal, part of the recovery process. So we can see like the first sentence is a very polite one, like I understand your concern. And then in the second sentence, we have going to direct to the answer, which says that this is a normal part of the recovery. And if we continue reading, after tonsillectomy, the body needs time to heal and remove any remaining tissue or debris from the tonsils. This can cause swelling and inflammation in the nasal passages. And okay, so we can see that these sentences just support the answer why it's normal. Okay, so we can see here like a full answer, which as the first sentence as a polite sentence for the patient, and then the answer, and then also explanation and support of the answer. And this is the answer from the data set, and we are trying to fine-tune a model to answer in this way. Okay, so it will be like a mimic the doctor. Okay, so we have our data set, we loaded it. Now we want to start the training. So first thing, we need to configure the LoRa parameters because we are going to use it. So LoRa R is for the rank. Okay, so I use it in this example 64. LoRa dropout. So dropout is a technique in deep learning for regularization, in which in some probability we remove some of the neurons. To be precise, we put like a 0 activation. And LoRa alpha, so alpha is like a weighting factor to give how much factor to give to the new adapted parameters versus the original parameters. So you can see here the LoRa alpha, for higher values of alpha, we will give more weight to the new adapted parameters for LoRa than the original weights of the model. Oh, I'm not sure what's the maximum actually. Okay. Yeah. Yeah, you should play with these hyperparameters. Usually for LoRa R, I know that people start from 8, 16, 32, like powers of 2. Also for the alpha. Okay, and then we have the LoRa config. Okay, and then we put where to put the final checkpoint of the training. So we need the path where to save the training result. And this is the class of training arguments. So here we define all of the arguments for the training, such as number of epochs. FP16 means the precision in computation time, batch size, learning rate, optimizer, and all of the things that you know from deep learning. And here we define the SFT trainer, which is a specific type of trainer because we are using a supervised fine-tuning. So we import the SFT trainer and we give it the model, the data set, the column in the data set. So we define it, the column name to be text. We give it the path config for the LoRa, the tokenizer, the training arguments, maximum sequence length will be the maximum sequence length of sequence in the training data. And packing is just an option for efficient combining. If you have like sequences which are short, so you can combine them together to be one sequence instead of adding a lot of padding. So this is more efficient. And then we use trainer.train to start the training. And this is optional, but we can put here like a path for the checkpoint. So if you have crash or interrupted training, you can continue from the checkpoint that you specify. And when you start the training, you will see this log. So in the log, you can see number of examples. So we have 3,000. You can see the number of epochs. So just for the example, I train it for one epoch. You have the train batch size. And then you have the total optimization steps, which is also the total number of batches in the epoch, which is the number of samples divided by the batch size. And in the last line, you can see the number of trainable parameters. So since we use a model with 7 billion parameters and our rank is 64, a quick calculation will give us that the number of trainable parameters is only 33.5 millions of parameters, which is much lower than all of the parameters of LLaMA 2, 7 billion. Okay, and last thing, here we want to save the model and then load it and export it. So to save the model, we use, again, trainer with save model. And here we specify the directory. So we save the final checkpoint. And we also save tokenizer config for the tokenizer and spatial tokens map. So these are like two JSON that the save model also save, because we need also the tokenizer when we load the model. And then here we use the autopath model for casual LLM from pre-trained and load the model from the directory of the final checkpoint. Of course, we can load model for not for the final checkpoint and take the checkpoint with some maximum performance, which is not the final one. Okay, and the next line, we have the merge model. So merge and unload gives us merging the LoRa adapted weights with the weights of the original models. And again, we use the pipeline and we reloaded the generator and we can make inference again. Okay, last thing we want is to export the model. So we give it a name and push to hub will give us, this is the command to push it to Hugging Face so other people can see our fine-tuned model. And okay, so I skip very important part, which is the evaluation, because I want to devote like a few slides only for evaluation, which is a challenging topic in LLMs. So of course, you are not going to push to Hugging Face a model that you didn't evaluate. You first need to be very satisfied with the results. And okay, so let's start talking about evaluation. So in general, for generative models, the evaluation is a challenging task. And this is because it is not necessarily exact match anymore. So for example, in tasks like classification, sentiment analysis, or name entity recognition, where we have like a discrete number of classes. So what we did is just, we compared between the ground truth class and our predicted class. But right now it's not the case. We have LLM that generates some text, and we have ground truth text, and we want to compare between them. So this is very challenging because there are endless possibilities to generate a good answer. And also there is no one correct answer. Okay, so before talking about the different methods for evaluation, what are the different aspects we should consider before we deploy an LLM? So first, answer relevancy, which determines whether an LLM output is able to address given input in informative and concise manner. The second one is correctness, which determines whether an LLM output is factually correct and based on some ground truth. This ground truth is sometimes called reference. So we want our LLM output to be factually correct, some reference. The next thing is hallucination, which determines whether an LLM output contains fake or made up information. So this is a bit similar to correctness. But in correctness, I think we're talking about specific detail, like for example, for the question, who is the first president of the USA, if the answer will be another person, which is not Washington, another person or another president, so this is incorrect detail. But hallucination is like totally made up a new story which does not exist. So this is a bigger phenomena. And then we have the responsibility, which determines whether an LLM output contains harmful and offensive content. So we don't want our LLM to be aggressive, offensive, or toxic. Okay, so all of the four categories, I think they are general for every LLM, for every task. And then you have the fifth one, which is task-specific metrics, which is a tailored criteria that you develop for your use case. So for example, next week, I will show you how we develop metrics for our task in VideoLeap, for example. Okay, so in addition to the general aspects that I show you, you have the task-specific metric that you want to optimize for. Okay, now let's talk about what are the types of offline evaluation, automatic metrics and scorers. Okay, so we want to evaluate in offline. And of course, we can use human evaluation, which is reliable and accurate, but the downside, of course, it's that it's very expensive. That's why we are seeking for automatic evaluation. And in automatic evaluation, we have the traditional statistical scores, which are reliable but less accurate. So for example, you can see we have the character base and the word base. So let's take, for example, the Rouge metric. So in the Rouge metric, we want to compare between, so Rouge is usually used for summarization task. And we want to compare the summarized ground truth with the predicted summarization of the model. So in the Rouge metric, we're calculating n-grams, how many n-grams overlapped with each other. Okay, so the Rouge metric is not so good. It's very sensitive, for example, for paraphrasing, because it doesn't take into account the semantic meaning, because I can generate sentence with different tokens with the same meaning. But Rouge actually just looking at the specific n-grams and calculate the overlapping. So after these metrics, we had like models like BERT. So now I'm talking about model-based scorers. So with BERT, we can calculate the embedding of the prediction and the embedding of the ground truth, and then use cosine similarity, for example, to estimate how much we close to the ground truth. And this is better because it's more accurate. It takes into account the semantic. Okay, and after the BERT score, we have also other NLP models. I will talk about NLI. And in recent year, we have, it's very popular to have LLMs that evaluate LLMs, which is not so surprising because if you want to evaluate LLM, it's not so surprising that LLM perform better. And we can see the paper G-eval, which is only one of the papers with the idea of giving the LLM to be the judge. Okay, so this is very popular. This is what people are doing to bypass this complexity. But let's see how we do it efficiently. So first of all, let's talk about NLI. So NLI stands for Natural Language Inference. And this is a task in NLU, which stands for Natural Language Understanding. And this is a subfield of NLP. So this is an existing task and we use it for evaluation. Let's see how. So what is NLI? In this task, we need to determine whether a given hypothesis and premise follow, unfollow, or it is undetermined. So whether the hypothesis can be entailed from the premise, contradict the premise, or neutral to the premise. Let's see an example. If we have the premise, female players are playing the game, and the hypothesis is the game is played by only males. So of course, we expect the NLI model to give high probability for the contradiction label. Okay, and how can we use NLI model for evaluating the correctness and hallucinations? So first of all, we need to choose a fine-tuned NLI model. And then for every sample from our test set, so for example, we have our patient-doctor data set. So for every sample, we define the premise to be the ground truth. Okay, so the premise will be the response of the doctor that we have in the data set. And the hypothesis will be the generated response by the LLM. So this is the prediction of the LLM. And we will give it to an NLI model. So let's see an example. The premise here from the data set, it's common for children to experience nasal mucus and coughing after tonsillectomy. And in most cases, these symptoms are normal part of the recovery process, as we saw before. But now if our LLM outputs what is in the hypothesis here, your daughter's symptoms such as nasal mucus and coughing are not normal after tonsillectomy, these symptoms could indicate a serious complication and you should seek immediate medical attention. So if we will ask the NLI model, it will say very high probability with contradiction. And it helps us to understand that our model is not correct and hallucinate. So this is the idea of NLI, using NLI model as a model for evaluation of our LLM generated text against some ground truth. And the next idea is using LLM as a judge. So here we have the paper of Microsoft, NLG evaluation using GPT-4 with better human alignment. So this paper also called G-Eval, where we use the LLM as an evaluator for a specific task metric. So what we need to do according to this approach, so we need to give the model the task introduction. For example, here the task introduction is for summarization of a news article. And we need to give the model, the evaluator model, right? We need to give it the evaluation criteria. For example, here we define the evaluation criteria to be the coherence, which is the collective quality of all sentences. And then we ask the LLM, the evaluator LLM, with a chain of thought to fill some evaluation form according to the task information and the evaluation criteria. So we can see here, for example, the evaluation form that the LLM produced for itself. Read the news article carefully and identify the main topic and key points. Read the summary and compare it to the news article. Check if the summary covers the main topic and key points of the news article, and assign a score between 1 to 5. Okay, so this is the instructions for the LLM how to evaluate according to the task description. And then the LLM will get some input, which is the article to be summarized, and we'll get input target, which is a summary of another model that we want to evaluate, another LLM that we want to evaluate. And then it will fill this form and calculate the score of coherence, which is the metric we ask for. And what they found in their paper is that most of the times it outputs the score 3. And this is a bias. So how they bypass it, I think it's a cool idea and maybe useful. So instead of taking the token with the maximum probability, which is most of the time 3, so they look at all of the probabilities of the tokens, of the scores, and they calculated the weighted sum score. Okay, so in this way, they got something which is not always 3. They look at the other tokens and weighted sum the options. Okay, so I think this is pretty it. So we had like a fine-tuning overview lecture. You learned what is fine-tuning and how to fine-tune your model. I compared between RAG fine-tuning and prompt engineering, and I hope that now you understand which approach suitable to which scenario. And then we talked about how to fine-tune an LLM. I show you like a code example, and we talked about the challenging topic of evaluation, in which I think that the most popular approach right now is just use an LLM for evaluation, but not like straightforward with some chain of thought prompt or other frameworks. And next week, next session, we will talk about a real use case from Lightricks for the video leap, which involves fine-tuning, in which we implemented some efficient distillation framework, and also also submitted a research paper to EMNLP conference. So finger crossed. Okay, that's it.
Just one moment, everyone on Zoom. So I want to take Oren, of course. It's only the first part, and after the other one too. I send you the feedback form now in the data group and in the tech department update Slack channel. So please, please, please answer it. We don't have a lot of feedbacks, and it's really important for us and people who volunteer to lecture. Thanks.
שאלות, כן. כמה זה עולה לעשות את התהליכים האלה? Distillation? לא, כל הזמן.